Jeff, I'll turn it over to you.
All right, great. Thanks, Elliot. So now we're gonna jump into some of the standard measurement devices that test labs may have. So what type of product should be in every lab? Well, that's going to depend. That's going to depend on the type of lab that you have, the types of tests being conducted, and we'll run through some of those right now, as you see here below. So force measurement devices that would be load cells, different types of load cells, whether you're doing tension and compression testing, perhaps compression only, or even if you're getting into a multi-axis for additional measurements that need to be taken. Torque measurements that could be consisted of torque standards, torque wrenches, torque verifiers, even lever arms if you're performing some types of low-level torque testing. Weights and measures also, that would be things like calibrated, certified dead weights that you may use to perform, again, low force or low torque range measurements and calibrations. Calibration standards, reference standards, those would be more of your premium, like 1600 series, 1800 series, standard load cells or torque standards. Different test stands that you may have, whether you need to, apply bending loads, whether they're fatigue test type test stands. Maybe you're just pushing and pulling on something, so they're very basic test stand or durability test stand. Data acquisition systems, that can be anything from a signal conditioner if that's all that you require, maybe data loggers, or it could be recording software for your measurements. And then safety equipment, that could be things such as do you have guards and shields around your test stands? Now we'll get into some of the force measurement lab basics. So when you do run or have your test lab, you want to make sure that you have proper transducer selection, right? So you want to have, how is the sensor going to be mounted? Is it a threaded connection? Are you bolting it in place? What type of loads tests are you conducting? That will make a difference on how you mechanically connect the load cell into your test stand. The force magnitude, you need to know right what you're testing and how high are the loads going to be. You want to make sure that you have the correct sensor selected to make those measurements. Cycle count, are you doing fatigue tests? Are they very high cycle count? You want to make sure that you're selecting the correct standard for that. Make sure it's fatigue rated if you're doing fatigue testing. Maybe you're doing, your test stand maybe just pulling samples occasionally and only doing very low cycle counts, so you don't need fatigue rated. Form factor restrictions, do you have space constraints in your test stand? Do you need small compact size, or do you have room for larger sensors? Maybe you're doing compression only load, so you could fit a much smaller load cell in, lower height restrictions. Environments are also something to consider. Are you in a temperature, a thermal chamber? Do you need high temperature capability? Is it going to be used in the lab? Is it going to be used outdoors? Are there hydraulic fluids? Are there other salt spray, environmental conditions that need to be considered when specifying a load cell? And then additional measurements, are you going to be making, multi-axis measurements, and, do you need to consider extraneous load measurements? Testing types, you could be doing component level or subcomponent level testing, such as, doing a test on a shock or a spring or a subframe. Do you need to have, are you doing a much larger scale component test where you're going to be measuring on a shaker rig? And durability testing, are you doing durability of, say, a seat, a seat mount or a backrest, where you're just pushing and pulling on it until something breaks, and analyzing those results. Safety testing, such as seatbelt testing or airbag testing, where you need very specific sensors to be able to make those measurements. Crash walls is also an interesting one. That's where you would have an array of load cells, could be multi-axis load cells, where you can measure impact loads. General, is this yours, Elliot?
Yeah, sure, I can jump in on this. So some of the general challenges, considerations when you're looking at, and again, this is more specifically related to like a general automotive test type laboratory. Generally speaking, you're going to have to be worried about high cycle counts. So the concern there is going to be making sure that the load cell selection is correct to handle those high cycles, and you do not prematurely fatigue the load cell over the life of the test. Or perhaps you want to have a load cell in place that would be versatile and able to be used in additional tests further down the road, and tolerate the previous cycle count induced, in which case you may want to look at a fatigue rated load cell. Jeff touched on this in the prior slide, but load cell integration into the actuation system. How are you going to integrate it? Is it going to be, does your actuator have a male thread? Is it female thread? Is it horizontal? Is it vertical? How is that actuation string going to be supported if it's horizontal and you do not have the test underway, or it's not in place? Do you have straps in place to minimize bending moment on the load cell? A lot of different concerns around that. Another one we'll see pretty commonly would be environmental challenges. Anytime you have hydraulics, you're probably going to have a leak at some point in time, and some hydraulic fluid can be detrimental to specific load cell types. For example, our blue low profile load cells, they are susceptible to damage from some fluid. It can be very aggressive, take the paint off, et cetera, et cetera. So knowing that in advance, we can provide a special coating to prevent that from happening. Load cell ruggedization. That's another one where you have tests getting configured, tests getting taken down. Essentially, you're going to be setting up for multiple tests over the life of your equipment, and you're going to be moving actuators, moving load cells. It's not uncommon for someone to trip on a cable or kick a cable, drop a wrench. So the ruggedization of the load cell can be important. So you can do that a couple of ways. There's specific features you can add to the load cell, such as connector protectors, where you can actually spec in a load cell with the expectation that it's going to be in a rough environment. So maybe you want a welded stainless steel unit, things like that. Another one that can be very important is considering the off-axis and impact loading potential results on the load cell. So the off-axis part of that is going to be any extraneous load that the load cell is going to be subject to during a test. So while everyone does all they can to align load strings and test articles as best they can to have only axial load, there's always going to be some degree of misalignment. And perhaps in a lot of tests, there's no way to really control how much extraneous load there is, right? Either it's a cyclic motion that inherently has a moment in it, or it's just, you can't align it that well. So making sure you're considering the off-axis and extraneous loads when you're sizing the load cell for the test is very important. Impact loading is also one that also gets folks in trouble from time to time, where they don't know or can't control how hard an impact is. And a lot of times that impact force ends up being a lot higher than what is anticipated. So it's important to know that the duration of the event, not so much the problem, it's the amplitude. So it doesn't matter how long the load cell is subject to a load, it's what that peak amplitude is, and it has to be within that safe overload rating of the load cell. And of course, that off-axis rating also comes into play there, as it effectively lowers that safe axial. And we'll touch more on that later on. And then we don't want to think this is going to happen, but it should be considered. You're testing something, that something could break. What happens when that device under test does in fact fail? Is there going to be some sort of a ring occur in the load string? Some sort of a reversal of load, perhaps? Perhaps you've got something tied up in tension very tightly and it fails. What happens to that load string under that failure? You're going to get a ring back into the load cell. Is it going to push the actuator in the load cell into the ground? And of course, that's also another safety consideration there of, what happens when this fails? Do we have safety provisions in mind to make sure that the most important thing, that people are not injured through an event of that type? Some standard load cells that we see very commonly in the automotive test environment. I mentioned fatigue rating earlier. This is one of our fatigue rated load cells, 1000 series. So these are rated for 100 million fully reversed cycles. That's means you're going from tension through zero to compression back to zero would count as one cycle. So a lot of cycles, very long life, very rugged. You'll notice that this one also has a housing around the connector. This is always recommended in this type of an application, just an extra layer of protection for the load cell. You've got a lot of load cells floating around, actuators moving around. Want to make sure that there's no potential for knocking that connector off. These use all of our internally manufactured strain gauges, which are, of course, temperature compensated, very good performance. These are actually also, all of our low profile load cells are eccentric load compensated. So again, that's another way we provide better performance, is that these will reject extraneous and side loading, so you get better results in your axial load measurements. Temperature compensated, again, relatively low deflection. These are, of course, tension and compression, and these are, generally speaking, relatively compact in nature. Another good option for this type of testing, let me find my mouse here, REC, rod end type load cells. These are really good if you have an existing male thread on an actuator and you want to keep that same male thread on the load side of the load cell. So it's also smaller diameter than a low profile load cell. There are some trade-offs in that these, except we missed a bullet point on the slide here, but these are not eccentric load compensated. So you would have to make sure that these are more aligned, and just know that they are more potentially susceptible to off-axis errors. Thanks for your question there. These are all full bridge sensors, so millivolt per volt output with no bridge completion required external to the load cell. Other common automotive test lab environments would be like automotive driveline types of tests. Vary pretty widely. It could be engine or motor performance and durability, where they're going to be cycling a motor on a dyno for a long period of time, either looking for specific valve timing events in the case of internal combustion, or perhaps looking at specific either control strategy or motor construction in the case of EV. Not uncommon to see folks running very high cycle counts from a durability perspective. Could be working on lubricants or other components, trying to evaluate that. Another very common one that requires very high accuracy from a measurement perspective is engine or motor efficiency testing. Internal combustion, this would be testing different lubricants and seeing how they can improve motor efficiency. Could also be different valve timing events again. So looking for very, very minute detail there. From an electric motor perspective, they're doing power analyzation, where they're running the motor and either evaluating a control strategy, a programming strategy, or a new actual motor design. Driveline durability, another very common one. This could be in the internal combustion world, including transmissions, and also rear ends, axles, things like that. And then, of course, they have the same lubricant efficiency testing also occurs there, where they're going to run rear ends, transmissions, different driveline assemblies, and essentially they're looking for any efficiency they can find through different lubricants, different bearing designs, et cetera, et cetera. Component test, this could be down to and including bearings. It could be different gear mesh, all sorts of different tests there. But again, looking for very small, minute detail there where accuracy is very key. And then something we also see pretty frequently is accessory drive testing. We've got some specific products that actually use that. This would be the case here would be if you're trying to test a front drive accessory on, let's say, on a diesel motor. Perhaps there's a fuel pump on it, and they're trying to test how much drag or parasitic loss they're seeing from that pump assembly, or a power steering pump, or an alternator. Could be any number of things in that regard. Challenges, considerations. A lot of times, dynos can either use axial load cells or they can use rotary torque transducers. And once we start talking about rotary torque transducers, it's very important that people consider and determine what the peak torque rating needs to be for the rotating torque assembly. A lot of times it can be higher than anticipated, and you look at and the peak torques can vary widely from the average running torque of the assembly. So things to consider would be startup torques, stopping torques. So how fast is that assembly going to spin down? How fast is that assembly going to spin up? And what does the inertial mass do in relation to that peak torque? If it's an instant on motor, for example, and a very high rotating mass, that could really make that peak torque go up very high. And then, of course, service factor for the different drive types. If you have a diesel engine, for example, you can have a different peak torque rating than you would for an electric motor, given the actual torque profile of that kind of a test. Secondarily, you have to consider how you're going to get that transducer into that rotating assembly, making sure you have the correct couplings. And there's a lot of considerations there and a lot of ways to do that. Typically, we recommend smooth shaft type bores with clamping hubs, but some folks do prefer, keyed shafts, things like that. There's a lot of different considerations there to keep in mind. Signal requirements, essentially, what output do you need from these transducers to get back to your data acquisition system, or how are you reading that data back? Environmental conditions, is it over-the-road test or is it lab test? Those are two very different conditions and environmental ratings. So over-the-road test, for example, you might imagine testing on a long grade in Colorado in the winter, for example, salt spray, pretty rugged environment, versus a lab test where it's very controlled, able to keep the transducer isolated from any environmental effect, relatively stable temperature. So definitely things to consider there. Noise. Rotary torque typically seems to be more susceptible to noise effects. You've got different, perhaps electrical noise being transmitted from VFDs and different drives on the actual rotating shafts. And isolating the transducer from those can be very challenging. So making sure you've got a good grounding scheme put together and implemented is absolutely key. And then, of course, there's always mechanical noise in these test stands potentially as well. So how do you isolate? Is it electrical? Is it mechanical? Getting good grounding to get the best results, always key. Vibration, making sure that rotating assembly is balanced well. If you have a shaft that's not aligned correctly or has a balance issue, you can end up shaking the transducer more than it's designed to do, which can lead to failure. So making sure you have your rotating assembly balanced sufficiently for the application in RPM range. And then lastly, test article failure, touching on this again. What happens when that rotating assembly fails? Do you have provisions in place to make sure that, number one, people are safe, and number two, what's going to happen to the transducer in the case of the failure? How do you isolate the transducer from potential damage in that result, or when that may happen? We have a product here. This is our model Axial TQ. This is our telemetry torque device. We just talked about what happens when the device under test fails and you have an issue. This is designed to have a gap between the rotor and stator. So let's say you were testing a rear end and you've got a rotating motor on the front side, and you're inputting torque to the differential, and you've got an ATQ, a torque transducer on the input side and two on the output side. What happens if you break an axle shaft? and perhaps the output shafts start whipping around, right? This is designed so that you have essentially no contact between the rotor and stator, and it will tolerate a greater degree of misalignment than a standard transducer would. So that's what we call that's a crash-proof design. These are available in capacities from 100 newton meters up to 10 kilonewton meters. A lot of different output types. These have frequency outputs, current outputs, standard voltage outputs. You can actually take multiple outputs off of the output module. It's also designed to be interchangeable. So if you have a stator that or a rotor that actually does get managed to be damaged, you can actually just swap the rotor out real time, no rescaling required for the output module. So it's just swap and go. We've got a wide range of different coupling types and different solutions for shaft integration on these as well. So very good device. The Model T22 pulley type transducer, we were talking about the accessory drive testing earlier. This is a very common device to be used for that. This is designed to have a custom bore and key cut in the transducer, and then a custom pulley size bolt circle machine for your application. So essentially the customer tells us what they want from a drive side and what they want from a pulley side, and they're able to integrate this. And this is measuring the torque between the pulley and that center hub bore there. So you might imagine you could mount that on an alternator or a power steering pump, and you can measure how much torque that device is requiring. See, aerospace testing, another pretty common application type. Typical testing types here would be full-scale structural static and fatigue, where they have perhaps an entire aircraft, and they have it essentially instrumented, and they have different hydraulic actuators and load cells applying either peak static loads, or they are fatiguing it over a profile of standard expected flight loads. So they're essentially simulating the life of the aircraft through landings and different takeoffs, landings, cruises, different events in flight, things like that. So that's very common. High precision thrust testing, aircraft, jet engine manufacturing, could be rocket manufacturing, things like that, where they have to certify that the engine is going to meet a specific thrust rating, or perhaps they're doing research and development on a new design and trying to find more thrust. Aerospace manufacturing, things we see there would be tooling and assembly machines, where they have instrumented devices that are essentially assembling aircraft. Component validation, with the rise of a lot of the composites in modern aircraft, it's requiring additional validation that these components are indeed as strong as they think they are, and they're matching what their FAA is telling them. Landing gear testing, another very common one. Wind tunnel testing, where they have very high-end balances and maybe have load cells or other force measurement devices integrated elsewhere. And then MRO validation, where they're actually reworking and recertifying different aircraft components for repair purposes. Some of the challenges, considerations in aerospace type lab testing, typically speaking, it's going to be high channel count. So you're going to have a lot of load cells, a lot of channels. How do you validate which channel is which on installation? That's one we hear about a lot. Installation density, in terms of having a lot of load cells in a small area. So you've got a lot of signals, you've got a lot of space limitation, you've got a lot of cables to run, things like that. So some of the things we've seen done there are different ID strategies for specific channels. So TEDS chips are something that's we've seen used. We're not going to touch on the validity of how it's programmed, but essentially people can use different TEDS ID chips as channel validation tools. So maybe not pulling scaling data off the TEDS chip, but it will allow you to maybe read a serial number and a bridge, perhaps bridge A, bridge B, bridge C. And then essentially that saves you some time in your channel validation, because your data acquisition can just ping the chip and it knows which one it is. That can be pretty handy. Installation density, again, coming back to the load cell selection there, making sure that you've got a lot of load cells around, you've got a lot of rigging, people moving things around, making sure you have different protection strategies in place for cables and connectors. Connector protectors, again, come into play here. Environmental conditions can widely vary here, depending on the type of test. is the test outside, in which case moisture is a concern. Is it a vacuum test? Perhaps the thrust test at altitude. So different concerns there. But those are all things to consider. Moisture, for example, we can provide load cells with additional environmental protection. And there's some specific installation schemes that can be utilized to try to avoid moisture ingress to the load cell, making sure the connectors are oriented correctly would be one example, and some other things to consider there. Form factor versus performance. This is another push we've seen in the last couple of years. Our low profile load cells, their form factor is essentially driven by the performance. We designed the load cell to perform as absolutely best as possible. And that design has driven the form factor of the load cell. Load pins has been one of the devices that have been more common in higher force applications that in the most recent years here. And load pins are essentially it's a circular device designed to fit inside of an existing structure. And these essentially the dimensions or the form factor of the load pin actually drives the performance. So kind of the trade-off there is you get a much potentially more dense measurement where you can have more actuators in a small space and potentially greater peak forces at a small side, but you wouldn't have the performance of a low profile load cell. So some trade-offs there. But typically we've been seeing is as those force magnitudes get higher, those actual measurement resolution or accuracy requirements tend to decrease a little bit. And then input forces versus reaction forces. This is another one that's been increasing recently, where you have your input forces, where you have your actuators pressing on an airframe, perhaps. Traditionally, it would be just bolted down to a bed plate, and they're simply applying input forces. Seeing some drive in recent years that people also want to start measuring what those reaction forces are through the mount side of the airframe. So they're not only measuring the input forces, they're measuring the reaction forces on the mount side of the test. Some devices been more common recently. This is one of our 3-axis load cells. Again, could be suitable for measuring said reaction forces. These are essentially designed to measure forces in the X, Y, and Z axis. Very convenient in that they have 3 independent full bridges. So no exotic instrumentation required, just standard load cell inputs, ranges from 10 newtons all up to 500 kilonewtons, so pretty broad range. For what they are, a relatively compact size, so they fit well within existing applications. Low crosstalk, so the bridges are not crossing over into one another, and these are all, of course, temperature compensated. 6-axis load cells, this is the step up from the 3-axis product. This measures X, Y, and Z and the moments about each. Pretty broad range of force, relatively compact for all the different axes that they take. Low crosstalk. These work a little bit differently than a standard load cell in that they do not have a dedicated bridge output for each axis. Rather, we have either 6 or 12 bridges dependent upon the size of the transducer. And then we use essentially the crosstalk between the bridges to characterize the forces and moments, and then use a 36-term coefficient matrix to actually calculate those applied forces and moments. That may sound complicated. We do have an amplifier that essentially we program that matrix into, and you get a scaled analog output for each axis. Very straightforward there. Different torque transducers. These are nice for people that are working on integrated tools. Perhaps they're building up something to do a repeated task over and over again. So its spindle drive can be mounted into perhaps a robot head of some type and run down. Square drive, spindle, female square, things like that. Capacities 1 newton meter up to 500 newton meter. Very simple, plus or minus 5 volt output. A relatively short axial length, very stiff. And for a lot of installations, it can really simplify how you're getting the transducer in there. You've got a bolt pattern essentially to bolt the transducer up to test articles or tools, and that spindle drive helps eliminate the need for different couplings. Jeff, turn it back over to you.
Yeah, thanks, Elliot. So next we're going to get into geotechnical and civil testing. So in these types of testings, we have things like concrete or asphalt testing. That would be where you're actually going taking a sample of perhaps a roadway and conducting some type of physical test on it to ensure its integrity. And those many different types of ASTM tests for that. Also, soil testing has many different ASTM tests for it as well. That would be where you're actually testing like subsurface conditions for physical properties of like soil composition and such, like a cone penetration test, for instance, the CPT test. Other civil structural testing, that would be things such as like a bridge structure, maybe a building, arches, towers, that sort of thing. So larger scale, all of these are larger scale types of testing. Condition evaluation, is this going to be done in the field or versus in lab tests? So you need to be aware of that and spec product accordingly. Some of the next slide, Jamie. Some of the challenges and considerations when doing these types of tests, forces become much larger when you're conducting tests on structures. So as that becomes larger, right? The load cells become larger, they become heavier. How are you transporting them? How are you storing them? How are you using them? That's always a consideration and a challenge. Environmental challenges, if this is going to be used in the field versus in the lab, is it going to be subjected to elements or exposed to hot or cold temperatures? Pressures, for instance, when you're doing soil testing, perhaps the sensor would need to be compensated for pressure so that it doesn't have an influence to, pressures. Also, fluids, right? Is it going to be exposed to the elements in rain or submersed in water, for instance, if you're doing some concrete testing? And then how are you going to integrate it into the structure? If you're in the field and you need to do a measurement on a structure, and for instance, suspension bridge, and you need to measure or monitor the cable tension on the suspension bridge, you can't disconnect that, right? So you got to have a way to be able to do that in the field without doing any harm or taking the structure apart, if you will. Here's an example of one of the high capacity load cells commonly used for concrete testing, right? Compression only. It was designed specifically to be able to have a compact design and lighter weight so that it, so you're able to carry it, pick it up and move it if need be. It was designed with handles on the side so that you could do that. Much less mass, and is common for the core testing. Next slide, Jamie. These are the very high capacity, low profile load cells, very commonly found in structural labs for civil testing, imparting loads on very large structures. Again, they have the proprietary interface, temperature compensated strain gauges, eccentric loads compensated. So just overall very high performing, high capacity load cell. So the types of structural testing that can be done, right, is like your general push and pull. So that would be common to like material testing, where you're doing just tension compression, perhaps fatigue testing of a specimen. Design proofing would be where you're taking a component and testing it to prove out the design integrity. Will it withstand the design criteria that it was designed to? And life cycle and fatigue validation. So that's testing that would just have high cycle counts to ensure that it's can last and withstand what it was designed to in its life cycle. Some of the challenges and considerations here are, you want to ensure that your load setup is not imparting, any extraneous loads, any off-axis loading or bending. You really want to make sure that you're only applying the load that you intend to measure. The versatility and interchangeability. So that would be if you've got many different types of tests that you're doing, and you've got a variety of product load cells or torque sensors on the shelf. Are those suitable to be used in many different types of tests, so that you're not, you're getting the most value there. And then also instrumentation compatibility. Do you have the proper instrumentation? Does it have the proper inputs to take the signals from these load cells or torque sensors, and does it provide you with the proper outputs for what you need to do, whether you're recording it and so on? Elliot, back over to you.
Unmute myself there. So we've got some of the standard load cell types that are used in kind of the general structural test. It's kind of like the testing labs that never know what they're going to get next, right? There's going to be a lot of different test articles that come through. So it's very versatile test instrumentation and load cells. This is a really common one to be used, model SSM, relatively simple load cell, pretty broad range in capacities. It is fatigue rated, so very long service life, environmentally sealed. So if there is something that comes through that might have a challenging environment, it's going to tolerate that very well. It's a very good performing load cell. Normally these have a tension only calibration, and of course very good for use in tension. Let's see, one of our new load cells we're pretty excited about, kind of a similar vein to the SSM, is our model SSC, Super SCS type miniature load cell. Relatively compact design, capacity ranges from 50 to 1,000 pounds. Relatively high force for how small it is. It's environmentally sealed up to and including for submersion. So keep that in mind. Very economical. You're looking at a price point under $200 for the most parts. Relatively stiff, relative low deflection for its design. And the design is also relatively insensitive to off-axis loading, which is unique among most S-type load cells. See medical device testing, kind of a specific subset of different testing labs, things they could be doing, research and development, testing new designs, validating new designs, PPAP, FDA certification process, a lot of testing, a lot of time goes into that. Device life cycle testing. This is a really common application. Things that they be testing, stents, valves, catheters, orthopedic inserts. A lot goes into that for good reason. Challenges, considerations for medical device type testing. Generally speaking, we're looking at devices that are going to be tested at lower capacities. So lower capacities bring different challenges. Perhaps they're going to be more suspect to outside influence. So all of a sudden you're worried more about how the cable of the load cells restrained, how the load string is applied. The environmental condition can have relatively higher impact on your results. Typically speaking, you're also going to see higher cycle counts. So it's going to go from, perhaps you're testing a bridge abutment in your civil lab and you're going to test it once and you're done. So all of a sudden you need to do 100 million cycles. So different sets of requirements for cycle counts, typically speaking, going to be on the higher side. Submersion is also, as you might imagine, much more common in this type of testing. So considerations there, typically it's going to be submersion at temperature. So there's that to consider. Also, you want to make sure that the load cell you select is suitable for submersion. We do have some sealed designs that customers are able to protect the cable from submersion and are able to use it. Other folks need to be able to completely submerge the load cell into the bath for the test. So different load cell protection schemes required for each separate application. Separately, how do you integrate these load cells into your testing machine? Is it an existing machine you're trying to test and implement a load cell to measure a force in that machine? Or you design a machine that is using a load cell inside of it? Other really common requirement here, given the medical environment, stainless steel. It's essentially able to be cleaned, important there, and also hermetically sealed. Common product types we see for this type of testing, model SMTM, very small load cell, very compact. A lot of times you see load cells start getting this small. Mounting provisions begin to become a challenge. This is nice in that it has a female thread both on the top and the bottom, relatively easier to fixture. You're looking at a size that's 3/4 of an inch by 3/4 of an inch, so very compact, excellent temperature performance. Another common factor when you're looking at lower capacity load cells is how do you keep them from being overloaded? If, for example, it's a 5-pound SM load cell, has a safe overload rating of 150%, you're looking at 7.5 pounds. It's not a whole heck of a lot and relatively easy to damage the load cell. So selecting a load cell that has an overload protection scheme in it is important. This particular load cell is rated for up to 10x of its rated capacity and has actual overload stops EDM machined into the flexure, so it's going to shunt the load around the gauged area past a certain force level. Model WMC submersible load cell, very commonly used in the submerged type applications. Yeah, very compact load cell as well. These can be obtained with either male threads or female threads or male and female threads, depending on how you want to integrate it. And again, submersibly rated, very compact as well, and very, very good to be integrated into those submerged applications. And again, these are also available with overload protection. Some of the more specialized testing labs we work with, we've got folks that are doing metal coupon testing, and testing there could entail just a simple tensile strength test. It could be doing shear testing. Flexural testing is very common. Normally, they're just trying to analyze a material type. Perhaps it's a new heat treat. Perhaps they're trying to validate that a specific lot is functioning to expectation. Another subset here, tribology. It's friction. They're going to be applying a known load and then cycling a specific material against another material and analyzing those results. Load cells can be used there, are used there, I should say, to essentially apply that downwards force and the resultant force that's on the x-axis. Multi-axis load cells can be a good solution here because you get both the downwards force and the x force at the same time. Rheology, another very specific measurement type. Essentially, you're looking at a measure of viscosity, and you're looking for essentially an axial force and a resultant torque there. So very specific sensor subset. Tire testing, very common as well. Peel strength and bearing test. We also mentioned that in the automotive section, but there are specific labs focused only on those things. Challenges, considerations for those kind of testing labs. Typically speaking, the design needs to be unique for the application. So we get very specific sensors for that type of testing. Rheology, for example, would be an axial force with a resultant torque, or an associated torque, I should say. So you've got a multi-axis sensor designed specifically around the expected loads. And again, different considerations for multiple axes of measurement. Let's say you have an axial torsion transducer. You're probably going to want to bolt to a flange as opposed to a single thread. Single thread not going to work very well for a torque measurement where it's going to try to uncouple itself. And of course, we're trying to match the sensor to specific requirements. Maybe there's a vacuum requirement in a tribology test, and we have to make sure the sensor's not going to outgas. A lot of different options there. The bottom line is just make sure you're considering all those different requirements. And in the past, we've probably done something similar for someone, and we can help. Different type of devices here. These are really good torque transducers for people that need a through hole. Perhaps they need to run a cable through something. Perhaps they're running a drive assembly through that center. It's our Model 5330 hollow flange, very stiff torsionally, resistant to extraneous load. It's very wide footprint, which enhances that essentially resistance to that overhung moment, and relatively compact for the torque rating. Model T3, this is a pedestal mount torque transducer, very wide range of torques, all the way down from the sub 1 Newton meter up to about 10 kilonewton meter, shaft to shaft. It's a non-contact transducer. There are no slip rings to prematurely wear. Speed rating up to 15,000 RPM, and resolution down to about 16 bits. These are also available with speed and angle optical encoders if you need to measure either angle or speed. This is a load cell that's very specific. This is our model TXY. It's measuring X and Y forces, a very low crosstalk, very good performance linearity down to 0.1%. And we also manufacture a version of this that's going to have a Z axis as well. This is very common for tire type testing applications. There's a center bearing there that can be mounted so you can measure a downwards force and force at 90 degrees to that.